Okay, good day, everyone, and welcome to my series on Calculus 1. So today we'll be looking at the concept of limits of a function. So basically, we'll be looking at using the correct notation to describe the limit of a function. We'll be using table of values to estimate the limits of a function or to identify when the limit does not exist. So we will also look at using a graph to estimate the limit of a function. We will be looking at one-sided limits and also the relationship between one-sided and two-sided limits. In our next class, I'm going to start from section 2.26 and section 2.27. Okay, let us get started. So the concept of limits has been around intuitively for thousands of years. It was not until the 19th century that mathematicians developed a formal definition for limits. That's okay. So to begin, take a look at this function. In our previous math classes, we would say that this function, f of x, equals to x squared minus 4 divided by x minus 2. We'll say this function is not defined when, say, f of x is undefined. When x equals to 2, because that will make the denominator to be 0 at that point. However, we are not going to be giving a complete description of the function around that point if all what we talk about is that the function is undefined at the point 2. So the concept of limits allow us to study what is happening to the function around that point x equals to 2. For example, point 2.01, point 2.001, point 2.0001. Those points that are very close to 2, we can try to understand what is happening to the y value. The same thing with this function and the same thing with this function. So we would see in this case that as x, as the input gets closer and closer to this point 2, we can see that the y value is trying to get to a particular value. In this case, we will see that the input value 2, around this input value, we'll see that on this side, we'll see that the y value remains something around whatever the y value here is. Let's say 1. Okay, the same thing towards this side, about that x equals to 2, we will see that the y value is getting to a particular y value. Here also we can say 1. Oh, here is -1. So here is +1. Okay. Also, in this situation, we'll see that as x is getting closer and closer to 2 from this side, we'll see what is happening to the y value. Seems not to get to any definite number, right? It's going to infinity. And also, as we are studying that function around that value x equals to 2, not at 2 itself, because it is undefined at that point, but about that 2, we'll see that we can talk about what is happening to the y value. Okay. Now, note, if we only discuss what happens at x equals to 2, we give a very incomplete picture of how each function behaves in the neighborhood, in the vicinity of x equals to 2, meaning we need to talk about what is happening around that input, x equals to 2, not at that 2, but in the neighborhood of 2. So that leads us to an intuitive definition for limits. So from the figure above, we observe, for example, that as the input values approach 2, the functional values, that is the y values for the function, for example, the first one, approach 4. Let us go back to see that here. We see that as we try to get closer and closer and closer to this point 2, we'll see that the y value is getting closer and closer and closer to 4. This is 4. 1, 2, 3, 4 to 4. And also on this side, as we get closer and closer to 2 from this side, we'll see that the y value is getting closer and closer and closer to that limiting value, which is also 4. So what does that help us to do? So uh, we say that the limit of f of x, that is the limit of that function, as the input x approaches 2 is 4. So formally, we can write it as limits of that function f of x as that x, that is the input, approaches a particular number, in this case 2, we say that limit is 4. Or we can also write it as the limit as x goes to 2 of the entire function x squared minus 4 divided by x minus 2 equals to 4. Okay. Let us continue. From this, we can build an intuitive definition for limits as follows. So that is in general, not just that particular example, now in general. Let f of x be a function defined at all values in an open interval containing a, with a possible exception of a itself. A in this sense is, for example, 2 that we considered the other time. Okay? And let L be a real number. A real number. So if all values of the function f of x approach the real number L as the values x, which is not a, which is not that particular point, but the x values as you study it closer and closer and closer to that point a on both sides. If it approaches that number a, then we say that the limit of that function acts as x approaches that value a is that real number L. More succinctly, we can say as x gets closer to a, f of x gets closer and closer and closer and stays close to that value L, and which is the same thing as what I've shown you the other time. The limit as x, that input, gets closer and closer to that particular point, function is some number in general. So there are some strategies that we can use to evaluate limits of functions. We are going to consider these strategies one by one. The first one is to use the strategy I described earlier just by considering the functional values. So we'll use table of functional values. How does that work? So suppose we have a point here, let's say 2. So we have somewhere here, we have, let's say 1. We have 1. But 1 is too far from 2. We want something very close to 2. So on this side, we can consider something very close, say 1.9. 1.9 is close to 2. Very true. But there are closer number to 2 than 1.9. What of 1.99? Another one, 1.999. 1.99999, and it keeps going like that. So in all these cases, we will get closer and closer and closer to 2 every time. The same thing on this side, we can say, well, 2.1, we can say, okay, 2.01 or 2.001 or 2.0001 and so on and so forth. In every case, we are getting closer and closer and closer to 2. So to do that, all what you need to do is just subtract 0.1 from that A, whatever your A is, 0.01, 0.001, 0.0001. Those values will get you closer and closer and closer towards that A is. And then you are going to compute the functional value, f of whatever this is giving you. You're going to estimate the y value. It is the same thing as what we did here on the graph. We say as we come closer and closer, we are at every time looking at the y value, checking the y value, and we see it is getting closer and closer to this. For example, at this point, if we consider this point, at this point, it is about 3 point something, not up to 4. It's about 3 point, maybe 3.9 something or 3.8 something, not up to 4. So we keep going, but we can see that it is getting close to something, which is 4 in that case. All right. So the same thing on the other side, we will add 0. 0.1, 0.01, 0.001. You can keep going, but if you have even this 4, you should be able to see some pattern where it is trying to get to. Let us take example. So an example here is to find or to evaluate the limit. Now you should be able to read this now. The limit of sine of x divided by x as x goes to 0. Okay, so we want to find that limit, that real number that the function is trying to get to. Okay, now we will use the first strategy by just evaluating or creating table of functional values. So our x is 0. So we just subtract 0.1 there. We have minus 0.1, or another way to see it, this is where we have 0. So to the left-hand side, you can have minus 0.1, minus 0.01, minus 0.001, and so on. And to this side, that is positive, I have 0.1. A smaller number is 0.01. A smaller number, 0.001. Smaller number yet is 0.0001. Smaller one, 0.00001. You can keep going. And then you can, evaluate this, say sine negative 0.1 divided by negative 0.1. So if you put that in your calculator, then should be having something like this. And you can do everything. You can, you know, evaluate this, evaluate this, and all this. Now, one thing that is just computation, but there is an important thing that we observe. If you look at our results in this column, as we get closer and closer and closer to zero on this side, we will see that there is a pattern that we have. This is 0.99, 0.999, 0.99999, 0.99999. We will see that that value is trying to get to a particular number, which is 1. It is trying to get to 1. So we say as x tries to get to 0, our f of x is trying to get to 1. Okay? What of on this side? Again, as that x is trying to get to 0, getting smaller and smaller, trying to get to 0, again, we see that the y value is trying to get to 1 as well, right? So, since that is the situation, then we can conclude that we can make this claim. That is the limit of sine of x divided by x as x goes to 0 is 1. We can make that claim. And if you put this function, f of x, the function itself, equals to sine of x divided by x. If you graph this on your calculator or using decimals or whatever technology you have, you will have something like this. You will have a graph like this, and you will see that as x tends to 0, as x gets closer and closer to this point 0, you see that the y value is approaching this point 1. It doesn't get there, but it is approaching it. The same thing on this side. Okay. So that is that about that example. Moving on, this is another example. Okay. Evaluate the limit of square root of x minus 2 divided by x minus 4 equals to 1. Oh, sorry. Uh, I should not put this there. We want to find a limit. Find the limit of this. Okay. Using a table of functional values. Okay. Now, we are trying to get to 4. Our x is trying to approach 4. So x is 4, trying to get there. So again, just subtract 0.1. So we can have like this, 4. So on this side, we can have 3.9, 3.99, 3.999, trying to get to 4 from this side. So if we plug in this in a calculator, you can pause this video and try to evaluate that function at those points. So you can pause the video to do that. Let me try to get a few of them done. Okay. Yeah. So if you compute this, you should be having something like 0.251582341869. For 3.99, if you do that, you should be having 0.25, 0.2506445662. The next one, 0.250015 627. The next one, 0.25001563. This 0.25000016. And if you do this side, you have 0.248456 and so on. Here 0.24984394 and so on. The next one 0.24998437, 0.249984 and so on. 0.24999984. So again, as we get closer and closer to 4 on this side, you will see that the y value is getting closer and closer to a number, which is 0.25. And also on this side, we'll see the same pattern. It's trying to get to 0.25. So we claim that it is safe to claim that the limit of that function as x goes to 4 is 0.2. Answer. So, and if you graph it, if you use any technology to graph it, then you will see that on both sides, as x tends to get to 4, the y value is trying to get to 0.25, even when that point is not there. The reason being that we have already seen that, well, we cannot plug in 4 here because it is going to make the O function undefined. So that function is not defined at that point, but we know what is happening in the neighborhood of that point. All right, so you should pause this video and try to estimate this, estimate the limits of this function. Now, the second strategy we are going to be looking at is estimating limit of functions using their graphs. So this is similar to what we have seen. This is a function in graphical form, g of x. So what is the limit? The question you need to ask yourself is, where is x trying to get to? X is trying to get to -1. Okay, here. Now, where is the function itself, the y values? Where is it trying to get to? Then you look at it on both sides again. So on this side, as x is trying to get to -1 from this side, we'll see that the y value is trying to get to this y value, which is 1, 2, 3. Can I say it is 3 here? On this side as well, as x is trying to get to -1, then the y value itself is also trying to get to this point, which is 3. However, the value of that function is undefined. I mean, it's not at this point, it is here. So we look into that later in this course. Okay. So we can make a claim and say that the limits, we can say that the limits of that function, which is g of x, as x approaches -1, is 3. Done. So it is possible for the limit of a function to exist at a point and for the function to be defined at this point. Yes, the limit exists at that point. If you look at what we had earlier, the limit exists, but that point, that function is not defined at that point. So we are saying that it is possible for the limit of a function to exist at a point and for the function to be defined at this point as well. But the limit of the function and the value of the function at the point may be different. It may be different as we have in this case. It is possible they are the same. It is possible they are not. Okay, we will have some examples in that regard as we continue. So you can make sense of this problem, evaluate the limits as x goes to 2 of the function h of x. So this is 2. On this side, if you look at it, it is getting to -1, trying to get to -1. On this side as well, it is trying to get to -1. So we claim that the limit is trying to get to -1. Okay. Now, two important limits. If A is a real number, and C is a constant, then we make a claim that the limit of a linear function x, as x goes to that particular number, A in this case is A. Look at this. A linear function. So if this is 1, this is 2, this is 3, this is -1, -2, -3, and so on. For a linear function, when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3, and so on. So let's say we are picking point 2. As x goes to 2, what is this function trying to get at? It's also trying to get to 2. What about 3? As x goes to 3, the function itself is also trying to get to 3. As x goes to 1, the function itself is also trying to get to -1. So that is why we say it behaves this way. And if it's a constant function, for example, let's say a constant function, f of x, let me give example. F of x, let's say equals to 1. So we draw it this way, right? Now, at any point of x, let's say 1, 2, 3, -1, -2, any point you want to test, as x approaches 2, for example, from this side, approaches 2 from this side, the y value stays the same. It is 1. As x tries to get to -1 from this side, tries to get to -1 from this side, the y value stays the same. It is 1. So that is why we say the limit of a constant function as x goes to a particular number will give you that constant value. So please keep these two because we'll make reference to these two concepts as we continue. Okay, now let us talk about the existence of limits. The existence of limits. When do we say a limit exists? So let us look at how to evaluate a limit that fails to exist, or let us look at an example of a situation whereby the limit of a function fails to exist. A good example is the function of sine 1 over x as x goes to 0. Again, let us use table of values. So now, look at this. You know how to pick those points now, like the 0.1, because we are trying to get to 0, okay? And on the other side as well, 0.1, 0.01, and so on. Now let us study the y value when you plug it in here and use your calculator to evaluate that. Here we have 0.54, 0.50. All of a sudden, we go to negative 0.82. All of a sudden, we are back to positive. Go back to negative, back to positive. What about on this side? So we cannot make any claim that this is the part, this is what is happening. Or we cannot say, as we are trying to get to 0 on this side, we cannot say that this is exactly what this value here is trying to do. We don't know what it is trying to get to, right? It keeps bouncing from negative and positive value. The same thing here, we say negative 0.54, negative 0.50, positive, negative, positive, negative, and it keeps going that way. Again, we cannot pinpoint that this is where it is trying to get to. We cannot find that single value like in the cases we have earlier, Where is our table? Here, we can see that it is trying, on this side, it is trying to get to a particular number. It's making effort to get to 0.25. The same thing with on this side. Also, on the previous table, we can see it is trying every time to get to 1, and also here to get to 1. And that is not what we have in the case here. So in this situation, we'll say, okay, graphically, we can see this is the behavior of that function. This is the behavior. We have our 0 somewhere here. So around that 0, we can see a lot of bouncing around between -1 and 1, bouncing up and down. So it is not going to a particular single value. So in that case, we'll claim that. So what do we write in that situation? We say the limit of that particular function, sine 1 over x, as x goes to 0. Watch this, guys. Our claim is that the limit does not exist. Please do not write equals to does not exist. Doesn't make sense. From English statement, limit of this does not exist. So you've already used that verb, does. So do not put equal to there. So just use this does not exist. So the limit of that function, sine of 1 over x as x goes to 0 does not exist. So that is our claim. If it cannot get to that single value, then we say it does not exist. Okay. Now you can pause this video and work on this. Use a table of functional values to evaluate this. You know what to do. We are trying to get to 2. So you only need to pick points from this side that are close to 2, points on this side that are close to 2, and you check the behavior, right? You check the behavior of the function, of the functional value. Then you report whatever you observe. Now, let us talk about one-sided limit. We've been talking today about looking on both sides, from here and from here. But let us study one of the examples we started with earlier. The function absolute value of x minus 2 divided by x minus 2. Again, at this point, x equals to 2. We cannot, this function f of x is undefined at that point. So, but again, we can study what is happening in the neighborhood of 2. Now, it is interesting to note that as x tries to get closer and closer to 2 from this side, the y value is -1. It doesn't even change. It's constant, -1. And then as x tries to get to 2 from this side, from the positive side, we see that the y value is what? Trying to get to 1, or it stays at 1. Okay. The other time I said for us to talk about limits, on both sides, they must be approaching the same value. Again, I will show you again. On our table, I will show you using table. On our table, on this side, it is trying to get to 0.25. On this side, it is trying to get to 0.25. Then we say the limit is that single number that we called L in our definition. Also on graph, we can see as we move from this side, the graph is pointing to trying to get to this particular y value, which is 3. We make our claim. But now we are talking about one-sided limits. That is, in a situation like this, when we look at a side, the value that that function is getting at is different from when you look at it from the other side. This is what we say. We will say that the limit does not exist. Please listen carefully. We will claim that the limit of that function, the limit of that function as x goes to, let's say, in this case, 2, we will claim that it does not exist. Please listen carefully. We will claim that it does not exist because it is not true. It is not approaching, or it is not getting, it is not trying to get at a single value. For example, here it is trying to get -1. On this side, it is trying to get to 1, right? From this side. -1 and 1 are different values. So we will claim that the limit does not exist. However, we can talk about one-sided limits. And now we will define one-sided limit as follows. That is, look at it, guys. We can look at the limit of that function as x goes to 2 from below. That negative you see on top means as you look at it from the negative side. Or now we can talk about, okay, in this case now it is -1. And we can also talk about the limit as x goes to 2 from above or from the positive side of that function is +1. Now, guys, these are one-sided limits. But the limit of that function itself as x goes to 2 does not exist. Why? Because the limit, because the limit from the left, because the limit from the left is different from the limit from the right. I hope that makes sense to you. So since -1 is different from 1, we say the limit from the left is different from the limit from the right. So that means one thing, that the limit as x goes to 2, look at it. I do not put from the left or from the right on it again. I just say 2. So it implies that the limit as of f of x as x goes to 2 does not exist. But we can talk about the one-sided limits. I hope that makes sense, guys. Moving on. So we say we define two types of one-sided limits, limits from the left, limit from the right, which exactly is what I've explained here. So you can pause this video and just read all this. That is exactly what I explained here. So please, the sign you have here is just telling you the direction. It's telling you the direction because sometimes you can have something like this. X goes to, let's say, -2. This. Oh, wait, what is this? So the sign here is just telling you the direction from the left or from the negative side. Why, if you have plus there, it is telling you from above or from the right. Okay. So please go through this. Read that. Now, let us evaluate one-sided limits. Evaluating one-sided limits. Um, so let us consider this piecewise function. You know what piecewise functions are at this point? Now, look at what we want to find. A one-sided limit. How do I know? Because of this sign. I have it here. And this, I have it here. Okay. Now, look at our piecewise function. It is already defined here for us. That function is x plus 1 if x is less than 2. And it is x squared minus 4 if x is greater than or equals to 2. So, how do we find limits from the left? Limit from the left for this. So, limit of f of x as x goes to 2 from the left. Now, if you look at the piecewise function, we are going to consider this part of that function. How do I know? Because our x is less than 2. If this is 2, this side, this is where we have x less than 2, right? So it means this function, x plus 1, is what we are going to consider. And from above, it means when it is more than 2 from above, so we'll consider these parts. Okay. And now, if we go to table of values, just do the same thing we've been doing and adding, how to pick that, right? 1.9, 1.99, as you get closer and closer to 2 from the left, right? From the left. So pause this video and find and enter the values for all these and see something for yourself. 2.9, 2.9, 2.9, 2.9, 2.9, 1, 0.0501, 0.001, 0.000, 0.000, Okay, so this is what we have. Now, we can see that on this side, as x approaches 2 from the left, the function value is trying to get to a single number, which is 3. And as x tries to get to 2 from the right-hand side, from above, from the positive side, this y value is trying to get to a single number, which is 0, right? Reducing, trying to get to 0. So we can say the answer here is 3 and the answer here is 0. In summary, folks, we can talk about one-sided limit for this function. We have just seen it. However, since 3 is not the same thing as 0, we will say the limit as x goes to 2. Look at it. I do not put any sign on it. That means I'm considering on both sides of that function, f of x. What do I write? Does not exist. I can only talk about the one-sided limit, not the limit at that point. Okay. All right. So if you grab that function, the function we just have here, where is it? This piecewise function, if you graph it, you have something like this. And clearly we can see that as x tries to get to 2 from this side, the y value itself is trying to get to 3. And on this side, as x tries to get to 2 on this side, the y value itself is getting closer and closer to 0. Okay. All right. Again, please pause this video and use a table of functional values to estimate the following limits, if possible. They are one-sided limits from the left and from the right. And what conclusion can you make? If you have the same answer, it means that the limit as x goes to 2 of that function is that number because they are the same. But if they are not the same, you will say does not exist. However, there should be some value for this. So pause this video and solve that. In general, we want to relate one-sided limit to two-sided limits. It's what I've said, and I've used it. In general, we'll say if f of x is a function that is defined on all values in an open interval that contains that a you are trying to get to, with the possible exception of a itself, right? And let L be a real number. Then look at this, guys. We will say the limits of that function as x goes to that number a is that real number L. If and only if and only if the limit from the left of that number is what? Is that single number. And the limit as x goes to that number from above of that function, if it is the same as that single number L, then we say this is the case. If they are different, then we say, let me put it here. Otherwise, we will say that the limit as x goes to a of f of x does not exist. So this is where I'm going to be ending this video. For now, we will continue from there next class. I hope you enjoyed this video. So look forward to watching the next video on this series. Thank you for watching. Bye-bye.